Welcome to today's keynote for the National Industrial Conference Board. We're going to dive into a critical challenge facing modern industry: smart manufacturing's execution gap. Many organizations invest millions into advanced technology stacks only to find that their operational reliability hasn't moved the needle. Today, we'll explore why technology alone is not a silver bullet and how we can bridge the gap to true reliability. Let's start with what I call the boardroom paradox. It is entirely possible and increasingly common for a plant to be digitally advanced with the latest sensors and dashboards, yet remain operationally fragile. Having data is not the same as having a stable, predictable operation. To illustrate this, consider a composite scenario. A company invests heavily in capital, sensors, cloud analytics, and digital twins. The technology works. A signal appears showing an anomaly days before a potential failure. However, despite the signal being seen, the line still stops. Why? Because there was no accountable decision made, no executable job created, and no verified intervention. The technology did its part, but the execution failed. This leads us to our core thesis for today. Technology creates capability, but only execution converts that capability into actual reliability. One is a potential, the other is a result. When we look at this problem, we find we are often answering two different sets of questions. The technology questions are about sensing, analyzing, and connecting systems. But the execution questions, the ones that actually prevent downtime, are about who decides, what work is created, when it can be done, and how we verify the risk is gone. If you only answer the first four, you haven't solved the problem. Ultimately, what the board is buying isn't a software platform. It's a controlled reduction in operational exposure. They are looking for safety through available safeguards, throughput via stable flow, smarter capital choices, and the trust that comes from credible, traceable control over the entire operation. In our first section, we'll examine the investment illusion, the mistaken belief that installed capability automatically equates to realized performance. When a project is funded and celebrated, we usually see this visible technology stack: the edge sensors, the data core, the AI intelligence, and the mobile experience. This is the shiny part of smart manufacturing that occupies the majority of project meetings. However, there is a much less visible reliability system that must exist for that technology to matter. This includes asset strategies, trusted context for signals, clear decision rights, work readiness, precision execution, and closed-loop learning. Without these 6 pillars, the technology stack is just an expensive ornament. The result of neglecting that invisible system is being data-rich but action-poor. The execution gap becomes painfully visible at the point where digital evidence needs to become physical work. We must remember, an alert is not a decision, and a decision is not a ready job. Value leaks out at every handoff. From the moment a signal is seen to the moment the risk is proven to be reduced, there are 6 critical steps. If any handoff lacks urgency, context, or ownership, the investment loses its value. This is why pilots often fail to scale. Pilot theater happens in curated environments with expert attention and clean data. But plant reality involves mixed asset ages, competing production priorities, legacy systems, and the messy reality of shift turnovers. Vendor demos almost always stop too early. They end when the risk is identified on a dashboard. But in the plant, the real work is only at its midpoint then. The value only ends when the risk has been physically changed and the learning is captured. This brings us to our first board-level insight. Stop asking if the platform is live. Start asking if the reliability loop is closed. Let's look at a composite incident. The orphan alert. An anomaly is detected on day -12. It's acknowledged on day -9, but with no owner. A maintenance window is missed on day -4 because no work package was ready. By day 0, the bearing fails. Technically, the smart system worked, but the execution loop was broken. Section 2 explores the anatomy of this gap. We need to understand the 5 interacting systems that determine whether intelligence actually becomes reliability. The execution gap isn't a software bug, it's a system design problem. It involves technology, process, people, governance, and asset context. If you focus only on the T, the other four will eventually pull the system down. The orphan alert pattern shows how a valid signal loses its owner at every organizational boundary, from the model to the analyst, to the engineer, the planner, and finally operations. Each step is an opportunity for the ball to be dropped. A major silent multiplier of this gap is the asset hierarchy. If identity is weak, meaning tags, ERP numbers, and historian paths don't match, the analytics and the work history can never be joined. You end up with fragmented learning and untrusted data. Simply labeling something a critical asset isn't enough. We must define the specific function, the failure modes, and the proactive tasks. Criticality without failure modes is too coarse for a digital model or a maintenance planner to act upon effectively. Context is everything. The same signal, like a vibration shift, can mean a product change or a bearing failure. Without operating context, your smart system will generate a cry wolf effect that destroys trust. To bridge the gap, we need a formal alert to work transaction. This should be a minimum evidence package that includes the observation, the diagnosis, the consequence, the required action, and, crucially, the latest safe time to act. Decision rights should be based on the strength of evidence and the severity of the consequence. High-consequence events with weak evidence require escalation and confirmation, while low-consequence, high-evidence events can be automated or bundled. We also need to track latency as a reliability variable. It's not just about how fast a model detects a fault, but how long it takes to decide, plan, get access to the machine, and finally verify the fix. This elapsed time is where the real risk lives. Precision work is essentially the physical part of the algorithm. A model's recommendation is worthless if the physical intervention is done incorrectly, with the wrong parts, poor assembly, or undocumented settings. Readiness determines if a maintenance window is usable. A great digital recommendation can expire while a job sits waiting for parts, permits, or qualified people. If the work isn't ready, the window is wasted. The loop shouldn't end at work complete. That's just an administrative status. We need verification, capturing the as-found state, confirming the as-left condition, and following up to prove the asset is stable. This is how we actually learn. Human factors are the invisible environment. Reliability work happens in noisy, high-pressure situations. We must design for maintainability and recognize error-likely steps in reassembly or shift handovers. We must also balance digital ambition with OT constraints. High-frequency software updates and cloud connectivity must coexist with the reality of legacy protocols and restricted change windows in a secure industrial environment. The second board insight is simple but profound. The gap isn't caused by change resistance from a staff. It is usually the result of an under-designed operating system. Now, let's look at how we design the reliability conversion system, the full loop from sensing to verified learning. The closed reliability loop consists of 7 control transitions. Each transition converts information into a change in physical risk. If any of these 7 steps are missing, the loop is open. For every transition, we need 5 controls: a standard for input evidence, a named owner, a time boundary or clock, clear decision criteria, and a record for traceability. This is how you manage a process, not just a project. What goes into the evidence package? It needs the unique asset identity, the observed change, a hypothesis on the failure mode, the consequence of an action, and a specific recommendation. This ensures the planner isn't guessing. A triage policy helps manage the flow. By plotting consequence against evidence quality, we can determine whether to act urgently, monitor the situation, or use a standard response. Before scaling any technology, we need a use case charter. This defines the expected outcome, the boundaries of where it applies, the control workflows, and the proof required to verify value. Asset strategy should be the demand signal for digital. You start with the risk and failure modes. Then you determine if there is a useful warning window and a feasible intervention. Only then do you select the technology to detect it. Data quality gates are essential. No model should run faster than its context. We need to ensure identity is mapped, time is synchronized, Operating state is known, and the sensor health itself is monitored. Integration is key. We must avoid creating a second inbox for workers. Analytics alerts should flow seamlessly into the existing system of work, the CMS or EAM, where planning and scheduling already happen. Decision rights must be clear. One accountable role per decision. Committees can advise, but a named role must have the authority to accept, defer, reject, or escalate a recommendation. We also need fallbacks. When the digital path fails, due to sensor loss or cyber isolation, there must be an operating fallback like manual inspections or conservative decision rules to keep the plant safe. The planning readiness gate ensures a recommendation only hits the schedule when it is actually executable. This means the scope, safety controls, resources, and operational windows are all aligned. The physical layer of digital reliability is the execution standard. This means capturing as-found evidence, following the specified task with precision, and recording as-left evidence to prove the fix worked. Verification happens at 3 levels. Did the asset condition normalize? Did the process flow improve? And did we update our strategy based on what we learned? If we don't check all 3, we aren't truly closing the loop. We must govern analytics with the same rigor we use for safety-critical instruments. This means version control, audit trails, and human oversight. AI governance in manufacturing shouldn't be one-size-fits-all. It should be risk-based. Our third board insight: scale the closed loop, not just the number of connected assets. Connectivity without a closed loop just creates more noise. In Section 4, we'll discuss the operating model and governance required to make this conversion a managed business process. This is a cross-functional team effort. It requires input from operations for context, reliability for failure logic, maintenance for execution, engineering for technical authority, OT for secure architecture, and finance for value tracking. Decisions should happen at the right tempo, from shift-level exception control to weekly work conversion, monthly learning reviews, and quarterly portfolio governance for the board. Your KPI tree should balance lagging outcomes, like availability, with leading indicators, such as alert disposition time and post-work check completion. This tells the true story of your reliability health. For the board, we suggest a 7-question dashboard. It focuses on exposure, conversion, latency, and learning. These questions move the conversation from, is the tech working, to is the business protected? We must also be honest about value. Potential value is an estimate or a vendor's business case. Realized value only exists when an approved action has occurred, the condition has changed, and the benefit is sustained. Workforce adoption isn't about training videos. It's a design outcome. Trust is built when frontline experts help co-design the system, when they're given the capacity to do the extra work, and when they see visible feedback on their actions. Scaling can fail in several ways. Cloning without context, connecting endpoints faster than you can manage them, or centralizing analysis while leaving local execution ambiguous. Avoid these common traps. Every use case in your portfolio should face a gate. Scale if the loop works, repair it if the gap is fixable, or stop it if there's no credible path to conversion. Don't let ineffective pilots run forever. Our final section outlines the roadmap, from pilot to sustained performance. In the first 90 days, your goal is to prove the operating system. Start with one value stream and a few failure modes. Focus on exercising real cases and fixing the controls before you try to expand. Over 12 months, you move from closing one loop to standardizing the pattern, replicating it across sites with local context, and finally institutionalizing it into your capital governance. Measure your maturity based on capability, not just tech. Are you just visible where signals exist, or are you adaptive where your entire strategy improves through governed learning? Let's look at a practical example of a bearing risk use case. We sense the trend. We make an engineering disposition within a shift. We create a ready work package, and we verify it with a comparable recheck after the repair. The result is a traceable control record. From the evidence to the hypothesis, the named authority, the scheduled job, and finally the proof. This is what an auditable, learnable reliability system looks like. To wrap up, here are 5 commitments we need from leadership. Name the outcomes, Fund the conversion capacity, assign clear decision rights, govern the evidence, and only scale through proven gates. In closing, remember that your competitive advantage is not more data. It is your organizational ability to turn trusted evidence into safe, precise, and verified action repeatedly and at scale. That is true smart manufacturing. This presentation is built on international standards and best practices from NIST, ISO, and the Department of Energy, ensuring that our framework for reliability is anchored in global industrial excellence. Finally, please note that the examples shared today are illustrative. Operational success depends on your specific asset context, your controls, and your local execution. Thank you for your time today.